Hello, everyone. My name is Catherine Mizrahi Rodriguez. I'm a fourth-year PhD student in the Smith Lab at MIT, and today I'll be walking you through my work on leveraging free volume manipulation to improve membrane separation performance of amine functionalized PIM1. First, to start us off, I'll go through some motivation. Natural gas consumption steadily increases every year. On the left, you can see the US natural gas consumption by sector, and on 2019, we reached almost 30 trillion cubic feet of natural gas consumption in total in the US. But CO2 emissions also continue to increase, and annual total CO2 emissions are plotted on the right, where you can see that as in total throughout the world, we've reached billions of tons, 35 billion tons in 2018 of CO2 emissions. These two metrics show us that it's important to continue to meet the demand that we have for natural gas consumption, but also it's critical for us to think of ways in which we can do it more sustainably and potentially ways in which we can actually remove some of the CO2 from the atmosphere in order to reduce the impact that we're already having in our environment. Implementing more energy efficient separation methods in the US alone could save millions of tons of greenhouse gas emissions on one hand and billions in energy costs annually. Membranes are an energy efficient and cost-effective alternative to separation technologies that rely on phase changes, such as distillation. Some advantages of membranes include limited maintenance and durability, as well as potential to decrease toxicity when used to replace amine adsorption plants. However, while they have many advantages, industrial membranes are currently limited to less than 10 polymeric materials. And this is primarily as a result of three key challenges. The first is an upper bound trade-off, which I will speak about in the next slide. The second is penetrant-induced plasticization or swelling of the polymeric material upon exposure to a polarizable gas at high pressure, such as CO2. And finally, physical aging or the densification of the membrane over time, which can change its performance and therefore yield it unusable for industrial applications. If we think of membrane performance, there are two key metrics to consider. The first is the permeability, which is a pressure and length normalized flux through the film, which can be rewritten in terms of the diffusion and the sorption coefficient in terms of the solution diffusion model. And the second is the selectivity, or the ratio of the permeability of the more permeable gas over the permeability of a less permeable gas, which can also be rewritten in terms of the sorption diffusion model as the product of the diffusion selectivity and the sorption selectivity. In 1991, Professor Robeson actually plotted a log-log plot of selectivity against permeability and found that there was an inverse relationship in the performance of materials to that date, and that there was a limit or an upper bound for these materials that they would not go above. So conventional glassy and rubbery polymers fell below the upper bound. And then in 2008, this was updated with emerging polymeric materials, where these fell closer to the upper bound, but they still had limited performance. So typically researchers aim to find and develop materials that have increased permeability and selectivity combinations. In 1999, Professor Freeman developed a theoretical basis for this upper bound plot. And in that paper, he also suggested two key metrics or key synthetic considerations that could be used to improve permeability selectivity combinations. And these included backbone stiffness and selective sorption. So on one hand, backbone stiffness can be increased in order to change the polymer packing structure and increase fractional free volume. And this can influence performance through the diffusion coefficient. Whereas on the other hand, by tuning selective sorption or the gas polymer chemical interactions, we can influence performance through the sorption coefficient. And many researchers, especially synthetic chemists, have looked at developing new materials to have increased backbone rigidity. These include things like canals, romp materials, and PIM polyamides, as well as the archetypal microporous material, PIM1, which I will be focusing on today. PIM1 is particularly interesting because it has a rigid backbone structure that results in inefficient packing with very high BET surface areas of about 800, large fractional free volume amounts, and this ultimately results in high permeability and good selectivity combinations. Because PIM1 is so rigid, it also has a degradation temperature that is very high but that is below its glass transition temperature, leading or having very desirable thermal stability for high temperature applications of any sort. And finally, PIM1 has this really interesting chemical moiety, a nitrile group that can actually be tuned in order to induce that second lever of selective sorption. So synthetic chemists have also looked at this aspect of functionalizing PIM1 in order to induce gas-specific interactions. And here we can see various functionalized PIMs from amidoxime, amide, carboxylic acid, thioamide, and tetrazole PIM. One thing that's important to consider here is that as these functional groups are added to the PIM, there can be an increase in secondary interaction, which actually leads to reductions in surface area and sometimes, many times, reductions in performance compared to the original PIM1 backbone structure and polymer. So here we actually have the original performance for a PIM1 sample. And when this is tuned or changed to various different functionalities, you can see that the permeability decreases for essentially every single sample. Whereas selectivity sometimes increases, but in certain cases, such as that of amine PIM1, the performance is completely destroyed after functionalization. And this is because of that reduced diffusion that occurs after increased secondary interactions, as well as the reduced PET surface areas. And in certain cases, it's really hard to tell what happened to sorption selectivity, which is the initial goal of functionalization for these materials. So in this work, we're really trying to think of a way of developing a method that can simultaneously enhance gas diffusion and access solubility enhancements in functionalized PIMs. So we looked specifically at amine PIM1, not because it had the worst performance, or not only because it had the worst performance, but also because it had the chemistry that would allow us to carry out the synthetic platform that we wanted to carry out. On one hand, amine PIM has secondary interactions that lower fractional free volume and reduce gas diffusion. And on the other hand, the amine PIM also has very high sorption affinity, which unusually partially immobilizes the CO2 and further reduces gas diffusion and CO2-based performance. So in our case, what we did is carry out a post-synthetic functionalization process where we protected the amine functionalized PIM with a bulky TBOC group to template free volume elements. And then these were deprotected either through thermal or acid deprotection methods. In the acid deprotection case, this was performed in solution, which can swell the polymer membrane. And in the thermal deprotection case, we simply put the film in an oven at 250 degrees Celsius in order to remove the TBOC functionality. And some of this work was really started by one of my colleagues, Sharon Lin, and I recommend that you look through her poster here at AICHI as well, work like this, but on polyamides. So we were able to carry out all of this functionalization, and here we can see the FTIR, where for PIM1, we have the nitrile group peak that is expected. Then when we look at the amine functionalized samples, you can see that there's the NH-WAG that's expected for both the regular initial amine sample as well as the deprotected ones. And finally, there's the carbonyl peak that's expected for the TBOC functionalized PIM. And we saw that there was also one of these peaks for the thermally deprotected sample, which made us very curious to think about what changes may be happening in the oven in addition to deprotection, which is something that we look into in the next slide. In addition, we looked at thermal analysis to evaluate the deprotection temperature for the sample, which is about 250 degrees Celsius, as well as how much we were able to convert into the TBOC functionalized sample. And it resulted in about 93% conversion, which was very high and high enough for us to see the effects that there could be with deprotection thereafter. When looking at NMR, of course, we wanted to really understand what was happening to our samples and whether we had identical chemistries for the deprotected samples. So here we have the original solid state NMR for PIM1, where the peak labeled 12 is indicative of the nitrile group. When this is functionalized to the amine version of PIM, there are 3 peaks that either shift or appear, and these are associated with the amine functionality. The TBOC also shows a very large peak, which is labeled peak 16 for the methyl groups on the TBOC, which was very encouraging that we had formed the correct material. You can also see the carbonyl peak 14, which appears at around 156 And that is associated to that carbonyl of the TBOC group, which again was encouraging that we had formed the correct material. After deprotection, however, you can see two interesting effects. One is that we do recover most of the chemical signals that are associated with the amine PIM. But also for the thermally deprotected sample, there's an additional peak that is labeled peak 14 that is not exactly at the same spot of the TBOC peak. So it should not be confused with residual TBOC functionality, but rather something else. And after looking at both ChemDraw predictions as well as some of the literature on potential reaction mechanisms that can occur after deprotection, we found that this might be urea cross-linking, where isocyanate intermediates or carboxylic acid intermediates during the deprotection process can react with the amine functionalized already deprotected groups in the sample and result in urea formation, which can be small urea cross-linking throughout the sample upon thermal deprotection. So of course, having known this and having synthesized all of these materials, we were really curious to see what the performance looked like. So here you can see that for all of this, we were able to characterize all of the samples in terms of pure gas permeation. And for the acid deprotected samples compared to the amine functionalized samples, there's no primary difference. There's an increase in permeability that is slight, and this can be associated with swelling of the material on presence of solvent for the deprotection process. And there's very slight changes in selectivity. Whereas in the thermal case, there's a boost in both permeability and selectivity that was very encouraging and that we think may be associated with the packing structure of the material. So we went ahead to better investigate that packing structure through pore size distribution analysis from positron annihilation lifetime spectroscopy. And here we can see the bimodal distribution for PIM1, and it's also plotted against or on the right, we have a table with the selectivity as well as the flow width at half maximum for the modes of highest intensity. When PIM1 is functionalized with the amine, there's a decrease in the free volume element diameter for the large size of the FBE, as well as an increase in the amount of these pores. Essentially, there's more smaller pores in the amine PIM, which results in higher selectivity. When the TBOC group is added, there's actually a shift in the complete landscape of porosity in the sample, where there's a boost in the amount of small pores. Both the amount as well as the average size decreases significantly. And this again results in a boost in selectivity for hydrogen, nitrogen. Now, when the samples are deprotected, what we find is that the acid deprotected sample shows an increase in the average free volume element diameter, which again indicates that our hypothesis of swelling of the material during acid deprotection was correct. And this can result in increased permeabilities, but not so much of an improvement in selectivity. And finally, we see that the thermally deprotected sample shows a narrowing of the free volume distribution, which we think accounts for that improvement in selectivity that we found. And for this to happen, we believe that we need the simultaneous deprotection as well as in situ cross-linking to take place. So having done this study, we were really excited to find that we could chemically engineer pores, that free volume modification could allow us to create distinct free volume element morphology in these samples for identical backbone chemistries. As you can see in the schematic on the left, it's a puzzle piece built from the exact same backbone, but slight changes in either the processing or the chemical structure of the sample can result in really large differences in performance. And one really encouraging aspect that we also found is that the BET surface area of the thermally deprotected sample was very close to that of PIM1 and higher than many of the other functionalized PIMs that we had seen in the literature, which indicates that this can be a really promising method for tuning the porosity of the sample and enhancing performance in materials that initially may not show such promising performance. Finally, I'd like to thank you for your attention and thank my thesis committee for their support and their scientific advice, as well as Smith Lab members who have been great even through this quarantine process, and funding sources.